Okay, today we're going to be talking about charging and discharging capacitors. So, let's consider the following circuit. Got a 10 mega ohm resistor and a 10 volt power supply, and we've got an ammeter, and we've got a capacitor. And a capacitor has a capacitance of 5 microfarads. And we're going to have a voltmeter over the capacitor. What you're going to do is set a timer, and you will measure how the capacitor, the voltage, the potential difference over the capacitor as time passes. And you'd measure potential difference every 50 seconds, or maybe less if possible, with the voltmeter. And what you'll find is you'll have a graph like this. You've got time in seconds, and then your potential difference. Now the supply voltage is 10 volts, and it'll go up something like this. Now we see that at the beginning the capacitance, the potential difference rises very quickly, and then it kind of slows down, and then when it reaches 10 volts it levels off. Now what we can tell from this, that the potential difference across the capacitor is going to increase as it increases in the circuit. The potential difference across the resistor is going to decrease, because we know V equals IR, and the current is the same at all points of the circuit. What we're also going to see, though, as the resistance, the potential difference over the capacitor increases, once it hits 10 volts, the current is going to stop flowing in the circuit. So if we were to have another graph, and this time we've got current in nanoamps over time, we're going to have it going like this. Oops. Switch to a nice smooth curve, and it'll trail off once the capacitor is fully charged. So we've got the opposite. The current graph is the opposite to the potential difference graph. Now the shape of these graphs are the same no matter what the resistance, the capacitance and the voltage are in the circuit. So the shape's the same. What will change, though, is the rate at which a capacitor will charge. So actually we'll get a new... So if we had, this is again looking at the potential difference over the capacitor over time, and the voltage is going to be the same in all three cases, but this time we're going to have different resistances. So what we see here, that because the resistance inhibits the flow, so this is just the resistance R. This is twice the resistance, and this is 4 times R. Now if you think about it, resistance inhibits the flow of the current. So if you've got a greater resistance, it's going to take longer to charge. I don't want to start at the origin, by the way. It's going to take longer to charge the capacitor. Similarly, which is also intuitive, the larger the capacitor, the longer it's going to take to charge. So again, it's the same voltage, so potential difference at the end is going to be the same. So we have this was for the capacitance of the circuit that we just drew. Then if it goes 2C and then like 4C. So the larger the capacitance, the longer it is going to take to charge. Now we see a similar thing happening when we discharge. So when we discharge a capacitor, we see a similar effect, but obviously switched. So let's look at the graphs that we would get, the shapes of the graphs that we would get for discharging a capacitor. So this is our potential difference. This is when the capacitor is fully charged and we discharge it. We're going to get the opposite shape. So it falls away really quickly, slows down, and this is time. And this time the time is in milliseconds. And the current is the same as the current shape for the charging. So if you think about it, when we hit discharge, the current is going to immediately start to flow. So it's at its peak and then it trails off. So this becomes really quite useful because we can have circuits where we want a sudden burst of current to be supplied really, really quickly and quite and strongly, in a way that we don't get when we have a battery. One such example is going to be a camera flash. So let's consider a simple circuit that you could have for a camera flash. So we have our resistor, then here we have our capacitor. We'll do 5 microfarads again. But this time we have a switch system. So we have, here is switch A, then we have switch B here, and switch C is going to be here. And switch C leads us to another circuit with a lamp, and if we're to put an ammeter in place, there we go, and we can have a voltmeter over our capacitor. So what happens is, just like the first circuit we looked at, we charge our capacitor and then we can put it at position B. So the capacitor is going to hold its charge whilst the switch is moved to position B. But then we come to want to take a picture, we need the flash. So when we click to take the picture, and we're set it for the flash to go off, the switch moves to position C, and what we see is a sudden discharging of current that will cause the lamp to shine very quickly, very briefly, as you see with a camera flash. An interesting point to note here is that we have capacitors have what's known as the time constant, and it's given the Greek letter tau, and it's a measure of how long a capacitor takes to charge and discharge. So if this is the percentage charge, and we're going to make this line here is like this is charging, discharge. So we start here, and then we go up to 100% charge, that's 100%, and then I'll go down here to discharge. This is over time. Now, let's think about some other uses, other applications of capacitors. So we've just spoken about the camera flash. And we can also, they can be useful as an alternative power supply in a power cut. So some capacitors you can have that the discharge is much slower, and so if you needed an emergency supply of electricity, say there was a power outage, and you needed just to protect your device or to protect not lose any data, a capacitor can give a short-term backup source of power, just to save that data or save your device if there's a sudden power outage. And another very important use is in AC to DC converters, and we're going to talk about that in more detail in a minute. And another one which is very important in our modern life is capacitive touch screens. So the screens on your mobile phone, your touch screens on your smartphones, these work with capacitors. So let's look at an AC to DC converter. Now these use diodes. Now we've not talked about diodes yet, and we're going to talk about diodes very soon in more detail in the next section. But we're going to talk more about the capacitor use in a bit. To begin with, let's look at the circuit that an AC/DC converter would have. So you've got your voltage, and you've got a nice alternating current coming in, and you're feeding it into a circuit here. And in this circuit you've got a setup of diodes. Now diodes are devices that only allow electricity to pass through them in one direction. So you've got a setup like this, and then you've got an output here, and an output here. And what you get from this circuit is a kind of chopped off alternating current. So it only has the positive part of the current. So it's like this. So this is your V out. So you've only got, it's a positive only potential, which is interesting and not at all useful in modern devices. So we need to take this and turn it into an AC, a DC current. So your DC current is like that, it's just flat. And so to go from this to this, we need to smooth this out. So what we do is we take this and feed it into another circuit. So we've got a capacitor, and we've got a in series with a resistor. So a capacitor, a resistor, and then what we get out here, we've earthed it down here, is something that looks a lot more like a DC supply. So it's kind of go as let me draw it a wee bit better. So it's going to be a bit wobbly, but it's nearly flat. So we've got a small ripple, but it's much more it's more straight than this positive only supply. What's happening is, I'm going to draw this again, our positive only supply, and we get a different colour. So what we do is, when the current comes in here, and as the current increases, the capacitor charges. So once it gets up to here, the capacitor is fully charged. So our capacitor is fully charged here, and then it discharges. So as it discharges, as the current decreases, the capacitor discharges, but then, so what we then have coming out here is a current that kind of drops off, but then by that point the current here from the input has started to increase and recharge our capacitor, so our capacitor gets back up to full charge. Then when this dips, it discharges again, but our capacitor has discharged, so the current flows here, and then the current input back here causes the capacitor to recharge. Then it drops when the input current decreases, the capacitor discharges, so we've got the current discharging, and then the capacitor charges again, then discharges. So this is our this pink line here is our ripple current, that is our output from this circuit. So I hope that makes sense.